Okay, hello everyone. Good afternoon. Today we will continue the partial derivatives, and I will show you some Okay, I think if you check the GeoGebra and find some graphs from the GeoGebra, if you see from the GeoGebra, you can check that you can have the uh, partial derivative illustrations, like for example this one, and maybe let me check the other. Let's see. Okay, if you see here, it has the sine graph like that, but it has two variables, x, y. So if we change our x, y coordinate, it's gonna change the level of the z, right? So if we are uh, changing our coordinate xy, we will have changed also the z level. Okay. Now you might see here on the top left is partial. We call this is partial of y. So we are having two kinds of partial, partial of x and partial of y. So if we change the x and maybe change the y, and let's say we illustrate the partial of x. This is partial of x. Okay, this is the tangent, the gradient. So as a summary for the partial, we will have two kinds of partial. Okay, two kinds of tangent. So this is the tangent of x. Okay, and you will also have tangent of y. But here, the tangent of y is 0 because we are only considering the functions is only sine x. There is no y in that matter. And when we differentiate, it will be 0. Okay. I will describe why this happened. So every time we are looking at two variables, we have this two partial of x and partial of y. And with those two, we will have a tangent plane like that. So I will explain all of the phenomenon here, why we have two partials and why we have the tangent plane. Okay. Okay, and you need to check frequently the classroom, the Google Classroom. Okay, I will put everything there for assignments, general announcement. Okay, and what I need you to do is check the Google Classroom. I just post the assignments for you. It's actually exercise to help you study chapter 12 and 13. Um, Also, I need to announce the um, for example, any information that you need to work on. Okay, let me set up the uh, okay, I'm posting inf informations and assignments on the Google Classroom. You might check later. Okay, and if I check the class, we have 22 students in the Google Classroom. So if you haven't joined, please join. Now we have 38 in this Google meeting. So there is only 22 on the Google Classroom. So this is the invitation to join. You can check the chat box. How to join? You need to create a GApps account. You need to create. And you can check on, I think, in the computer center website of NTUSD. You can check the how to create GApps domain account. Once you create that, you can access the Google Classroom, and I will post informations and assignment on the Google Classroom. Okay, so the Moodle will be on the general information. So all the details for assignment you need to check to the Google Classroom. Okay, and for next lectures after the quiz, I will start the lecture through the Google Classroom, Google Meet. Okay, so I will open the Google Meet through the Google Classroom, not by this link. Okay, so I will announce later. Okay, on Moodle. Okay, let's continue a little bit for chapter 14, the partial derivatives. So we have uh, finished the introductions for limits and continuity. Basically, most of the important points on limits and continuity, most of them all are similar to what we have done in calculus 1. Okay, like continuity, limits, all similar, but with additional that is more than one variables and so on and so forth. Okay. And now for today's lecture, I will be focused on partial derivatives on 14.3 and maybe 14.4, and a little bit announcement how to prepare next quiz. Okay. Okay. Now start with the 14.3 uh, partial derivatives. So we say this is function of x and y. Okay. Let me start with definition first. Okay. So if z is equal a function of x and y, then the first partial derivatives with respect to x and y are, sometimes your textbook will write the partial x like that and partial y. Okay. And the definition of partial x and partial y is based on our limit definitions as we have learned before. So let's just write limit, and it is similar with calculus 1. The difference, we are adjusting this to be having x and y. Okay. Okay. And then partial y. Now we are added the h to y. So f, then y plus h. And of course, this two need to be axis. So for the limit axis. Okay, let me start with how we operate the partial. Okay. Before going into detail of all the concept. So if I write functions here, let's say 3x minus x squared y squared plus 2x cubed y. Okay. If I want to look for the partial of x, okay, what we are going to do, we just differentiate with respect to x. Let's say 3x becomes 3, right? And then if we look at these two component xy here, we need to treat y as a constant. Okay. So x we treat as a variable. So this will be 2x, and y squared will be y squared because we treat them as a constant. And then plus this becomes 6x squared and y. Okay. So here treat y as a constant. And if we are looking for partial y, we need to treat x as a constant. So 3x becomes 0. And this will be negative 2. Let me write x squared and y. So this is from y squared. It's become 2y. Okay. That is what's happening. And then plus 2x cubed. So we treat x as a constant. We may also write down the symbols or the math equations. We can also write in terms of Leibniz notations. Or this also fine. It is the same definitions. Or with z. this all of the symbols is the same. Or maybe in your textbook they also mention to write F1 like that, or D1F, and if Fy is F2, D2F, and the rest will be similar. Okay, and it's up to you which one you are going to use as a written form. Okay, as long as you understand the basis of the partials. Okay. Okay. Okay, maybe another example. I have x, y. X, and then multiply with e with the power of x squared y. And the question is evaluate partial x, partial y at 1 and 2. And the other, if we have functions, you can try to check this part, the first one. Find fx, find fy, partial x, partial y. And the second one, if we have this, it's the same. We need to find partial x, partial y. Okay. Now I will look for the second one first. Okay. If you look for partial x from this sign from here, the general equation is sine of the equations. Right? Probably it's sine u, right? So this is basically a chain rule problem that are similar to what we have done in calculus 1. So first, we differentiate the whole thing to become cosine, and then write down all the terms that, and we multiply with the inside. Okay, so this part is just become 1 over 1 plus y because it's only with x. We differentiate with x. So this whole thing becomes cosine, and then 1, 1 plus y. Okay. And now the partial y. The same thing, we differentiate the sign and become x plus y, but we are differentiating with respect to y. Okay, this is the partial y. Now, if we look at the x here, we treat the x as a constant now because we differentiate with y. So x is still x, and then the bottom part is just like if you have 1 over x, this will be negative 1 over x squared, right? So this will be negative, and then 1 plus y, and then squared. Okay. So we will have cosine, or maybe I will write negative in the front. And you will see this is x, and then 1 plus y squared. Okay. I hope you get it. Okay. This is just a regular chain rule. Okay. Now this part, anyone want to try to check what is partial x and what is partial y? X is 6. Yeah. Any other answer? Yeah. Tong, you want to write the answer? Y is E. Okay. Okay, let me check. You can correct me if I'm writing wrong. Okay, so for the partial x, because we have x and ex, e to the x squared and y, so we need to do the product rule. Product rule. Okay, so first is we write, or maybe I will use the black color. So this, and then plus, and then plus 2x y, and then multiply by x, and then x squared, and e x squared y, right? Is it correct? Oh, yeah. Now x is 2 plus 4 ln 2. Yeah, that's correct. Fy is 2, x is, 2 plus 4 ln 2. Okay, correct. And Fy become x cubed, and then e x squared y, right? And we apply the coordinate, and this will become, so fx is e ln 2 plus 2 ln 2 e ln 2. This will be 2, so it will be 2 plus 4 ln 2. Yeah. And Fy is E ln 2. This is 2. Yeah, I think you need just to be careful when you plug in the ln2. Okay. Yeah, nevertheless, I hope at least, this part here, you get the the correct formula. Okay. Okay, that's just the example. Maybe later we can have some more exercise. Okay. I think if we have time, maybe on last 20 or 30 minutes, we can have some maybe chapter 12 or 13 exercise if you want. Okay. But let me continue chapter 14 first. Okay, the next part is the geometric part. Okay. The geometric part or geometric interpretations. Okay. If we have let's say we have point here, maybe A, B, and then we have let me make with green color. Okay, and then on this plane, let me mark this as this is our plane. Okay, let me use different color to check. Let me use blue, and it will so let me mark this as C. This is C1 and C2. Okay, so this plane is having a curve that lies on that plane. Let's say we have C1 and C2. Okay, and on that curve, exactly at this middle point, the intersection of the curve, we have okay, we have, let's say this is T1 and we have T2, the tangent. Okay, so this is what the geometric interpretations of the partial. Let me mark this point here and make it A, B, C. Okay. Okay, recall equations Z equal F X Y. These equations represents a surface. Let's say it's S. So this is S, surface S. Okay, like a plane. Okay, and P, the point P is lies on S, the surface S. If we fixing the y equal b, we restrict our observation to C1, right? And if we are restrict or look at x equal a, we restrict our observation to C2. Okay, this is what we have done in limit. Okay, so the middle point P here, the ABC, it can be approached from many curves. Right? It can be approached from here, can be approached from here, right? The way that easy to approach, if we set up the x and y equal to the coordinate of this point x, y, and then by doing that we can observe only this C1 and also only C2. Okay, so we only set up a point that will observe this curve. Okay, okay, I hope you get it. And then both C1 and C2 pass through point P. Okay, and C1 is the graph of functions when y equal b, right? So the T1, the tangent, its tangent is G prime A, or we can write also in terms of partial x. And on C2, let's say it's H, and we call it T2, the second tangent. This will be H prime should be B. Wait, H prime B, and this will be equal to partial y of A B. Okay. So as a conclusion, fx or partial x and partial y both can be interpreted inter in, interpreted geometrically as the slopes of tangent line at point P to, to the traces C1 and C2 of surface S in planes y equal b and x equal a. Okay, if you confused about the words here, let's just imagine when you have this point here, you will have a plane. Okay, so for example, x equal a, maybe a is here, and y equal b, b is here, and we can have a plane that is like that, for example, or for a plane like that. Okay, the point is, from the plane, we can trace the surface S become the curve 1 and curve 2. Okay, from that planes. Okay, from x equal A and y equal B. Okay, and then when it's intersecting the surface, we can set up a point in which both of them are intersecting as curve 1 and curve 2, in which this is the point P. And at this point, we can set up the tangent at that curve, okay? And that is our partial, okay? So this is our partial x, this is our partial y. Okay. Okay, now let me give you another interpretations from example. Find slope in, which means it in x direction and in y directions at this coordinate for the equations. Let me write the equations here. The equation is negative half x squared plus y squared plus 25 over 8. So finding partial x, it's just negative x and the other will be 0. Partial y will be 2y and the other will be 0, right? Oh, wait. I think to make it interesting, maybe this will be just negative. Okay, so it's also negative here. And we can put our coordinate. This will be negative half. And this will be negative 2. So what does it mean in terms of geometrics? Okay. From here, we can see negative half. Okay, this is negative 2, the partial y. And remember that this is, we can also write as dz over dx. And this is also, we can write dz over dy. Okay. So by these terms, I hope you get the idea. This negative half means z decrease 1 unit for every 2 units increase in x. Okay. And here, z decrease 2 unit for every unit increase in y. Okay. I hope you get the idea. Okay. Okay. So basically what we are going to do with all this stuff here, we need to find the slope in x direction and find slope in y direction, in which we know that this is dz dx and this is the z dy, or we can simply say partial x or partial y. Okay. Okay, that's the geometric interpretation. Maybe we will move later to explain more in details for geometric. But I will go to the next sections, the higher order and functions of more than two variables. Okay. Okay, let me make the new page. Okay, function of more than two variables. This is actually, long story short, it's similar. Okay, so if you have x, let's say xyz, what you are going to do is just limit and take the limit definitions. So the partial x from the three variables, that just means that we need just to add h on x-axis. And basically it's similar. Okay. If you want to take the more general approach, um, let's say if you have u is a function of n variables. So we are not saying how many variables we have, but it's as many as we may write. Okay, we can write u is functions x1, x2, x3 until some n. Okay, and its partial derivative with respect to xi, which means you can change this to x, y, z, etc. But I will just using x1, x2 to get the idea that it can have many as it can be. Okay, so let's write this partial derivative of with respect to the number of variables of x. Okay, it's actually a limit it's quite long. So f start with 1, and then let's say we have I minus 1, and then xi. Oh, maybe this is the plus h here, and then x plus 1 to okay, so you know the difference. Okay. And xn, and then minus the xi xn. And we can also write this in terms of other symbols. Okay. This is just to show you that we can have many variables as we can. Okay. Okay. Another things is we call higher order partial derivative. Okay, if we have the partial x, if we derive one more to the x. This is fx, right? If we derive one more time, it becomes fxx. Okay. If we have x like that, and we derive with respect to y, this will be fxy. Okay. How to write this is the inside functions there, and this is the second derivative. Okay. So if we also have dy, the partial y, we differentiate with x. How we are going to write is fyx. And if you have partial y and differentiate with respect to y, this will be fyy. Okay. Now let me give you an example and what we are going to see, the phenomenon that we are going to see. So let me write the equations. Okay. So the question is we need to find fxx, fyy, fxy, fyx. So let's start with the partial x. This will be 3y squared and then 0 and then plus 10x y squared. Okay. And maybe we can start with fxx. This will be 10y squared, right? If we start fxy, it will be 6y plus 20xy. Okay. Now if we start with partial y, this will be 6xy negative 2 plus 10x squared y. We differentiate one more to y. This will be 6x plus 10x squared. And if we differentiate with respect to x, this will be 6y, sorry, plus 20xy. Okay. Now what is the phenomenon? The phenomenon is we have this same results. Okay. Right? And this two we can write is equal, right? Now we have another theorem. It's called the Clairaut theorem. So if a function is a function of x and y such that fxy and yx, partial xy and partial yx, both are continuous on open disk. Let's say disk R or disk D is similar. Then every point in that disk will be okay, that's the phenomenon. And the Clairaut theorem is not only limited just only two variables. If you have more than two, like 3, 4, for example, if you look at f, let's say 3 variables like that, at some point you will have like x z z is equal f x f z x z f z z x. As long as the number, this is on 1x and 2z, all with the same combinations, 1x, 2z. Okay, so maybe f y z y z z f z y z f z z y is also similar. They will have equal numbers. Okay. Okay, that is the higher order of partial derivatives. In your textbook, they also giving you the terms partial differential equations. Basically, this is mostly for helping uh, equations on physics, for example. Like we have this is the Laplace. I won't get into details about this, but what I want to show you here is the partial derivative. It can be helping solving or simplify some physics problems, or even other mathematical notations problem. We can simplify with partial differential equations. Okay. Another tools that I want to talk about, I think your textbook didn't mention about that, is called the implicit partial differentiation. Okay, let me recall some theory from your calculus 1. Okay, if you have y equal f of x, okay, let's say we have x squared plus 2y equal 2x. If we are going to implicitly differentiate all the equation here, what we are going to do, we write ddx, right? ddx. Okay. What will happen? We just differentiate normally, like a regular derivatives. X squared becomes 2x, but y becomes dy over dx, and this is equal to. And you can, if you want to find dy dx, and you can find it, right? Okay. And now we have implicit partial differentiations. Okay. Now, in calculus 2, the idea is similar, but if you look at the equation, it is having at least two variables, right? At least two variables. Now, instead of ddx, what we are going to do here is to make it different. We are having this or this, right? Because we can have two possibilities. Okay, let me go into some example. Okay, so find slope in y direction of sphere at a point, this point. Okay. Now let's start by writing the sphere equations. Okay, what we need to find is the slope in y, right? Slope in y means we need to find this dou z over dou y, or partial of y. Or let me write partial of y, partial of y. Okay, now how to deal with this? When you meet the x, that's a constant, means 0. When you meet the y, that's your variables, so you need to differentiate that. But when you meet the z, this is the terms that actually similar with this y in the calculus 1. So because z is function of x, y, we need to treat z as y, but we need to add at the end that partial notations, and this is 0. So you can solve this. This is 2. It's equal negative y over z. Or if you look at the coordinate is, consider that this is negative half. Okay. This is quite, I think, quite practical and easy to use. Okay. So if you have difficulty on some partial problem, especially if you want to deal with physics, and you know that it is at least two variables problem, you can do this implicit partials. Okay, it's very easy. In practical, it's very easy. It's the similar way with calculus 1, but the difference is you need to define what functions you are dealing with. Okay? Here, in calculus 2, we can have many variables, right? We can have x, y, z, w, and etc. Can add more and more and more. But how to deal with the slope? Okay, at least two variables, is we can use these implicit differentiations. Okay. Okay, that's the implicit partial differentiations. Any question first? Partial differentiation of equation. Which part, Tom? This. Oh, that's just example. That's just example. Actually, whenever you have like because in physics there are many equations that can have partial forms. Okay, so that means we can actually solve that physics with the partial differentiation. Okay. Okay. Let me just take some intro for 14.4. And maybe we can have some exercise for chapter 12 or 13. Okay. So this should be about the tangent planes. Okay, from previous calculus. So in calculus 1, you are observing tangent line. Okay. Now you are observing the line becomes the plane. I think that is makes sense because before you have only function of x, and that is becoming a line, and now you have xy, right? Okay, let me start with the some illustration of the graphs. And let me make up the plane is like that. And we have a curve and we have the tangent. Okay. Let's say this is T1 and this is T2. And the point P in the middle. And this is curve 1 and curve 2. So we already talked about the C1, C2, T1, and T2. What I'm going to show you is the tangent plane. Okay, the tangent plane to the surface. Let's say this is the surface S. Okay, at point P is defined to be the plane that contains a tangent line T1 and T2. Okay, so if we are look at this T1 and T2, we can set up a plane. Okay, at least that is the plane. Or maybe let me make a little bit. Okay, so the tangent plane is actually having T1 and T2, or contains T1 and T2. And let me write the equations. Okay. From the chapter 12, we know that if point P is having x, y, z, x0, y0, and z0, it will be the plane equations. The plane equations will be, let's say we have A, and then plus B plus C and equal 0. Okay, now next step, let divide all with C. So uh, divide by C, divide by C, divide by C. This is just 1, right? And I will move this to the right side. But let me write the Z first and then equal. Now the right side become negative. Okay. Now if we let this negative A over C and negative B over C become some constant, other constant A and B, let's write this in terms of A and B, the small b. Okay, now remember, remember at the previous that I mentioned, remember that we make plane y equal b and x equal a. So similarly, let's take that approach and make it into the formula here. So when y is y0, that means this is becoming 0, right? And we have z equal a. Okay. And then when x equal x0, we have, okay, similarly. And from here, we can define that A and B is actually this is right, or partial x, and B is or t. This is t1, right, and t2. Okay. So suppose functions has continuous partial derivative an equation of the plane of the tangent plane to surface, the surface is Z at point P is Z minus Z0 fx Okay. Okay, for chapter 14, I will stop here, and the next thing is maybe some exercise. Let me check the. Okay. Okay, let me move to the next page to check the. Okay. Let me check the number. Okay. Okay. We can start with find the length of the curve. So length of the curve, and then find the curvature. This is number one. Number two. Let me check the equations. Okay, maybe let's say the simpler one first. find the normal vectors. Okay. I think there are questions for exercise today. By the way, you need to check the Google Classroom. Okay, Google Classroom. I put some informations. So what you are going to do for the information is you need to write down your name, student ID, and mention your calculus class, the code of the class, and send email to me from your GApps. Okay, from your not your from school email or your personal email, but from your GApps account. Okay, I already post in the Google Classroom. You can check. And also, I'm posting the assignments for you to check and having some exercise. Okay, let me show you. Please send from your name, student. Okay, this you need to send, but maybe later after the class. That's fine. Tonight also fine. But remember to check your Google Classroom, and because I need to add all your account for all the exam that we might have in the future. Okay. So do not send from your other emails. Okay. Only send it from your GApps account. Okay. I think several calculations a little bit long, right? A little bit complicated, complex. But actually, how you are doing it is not really that difficult. Because the difficulty is, I think, because it takes time to write. Okay, let me start from the first one. Okay, we need to find the length of the curve of this curve. The length of the curve, remember, let me write here, is this. Okay, so we need to find the first derivative. Okay, the first derivative. Let me move this to. Okay. So the first derivative, we get 2t and d squared. Okay, and the magnitude value. So we need to find the value first. So 4 plus 4t squared plus t with power 4. Okay. So my suggestions, okay, every time you see the arc length, like from the chapter 10, and then now we also see the arc length. Whenever you find these equations, do not panic. Simply because we have square root, we need to find a way that how to cancel the square root. The first thing, maybe we can factorize. So let's factorize this. So probably 2 and this 2 squared, right? If we check, it's correct, right? So let's write this as in our answer. So our answer will be 2 plus t squared. Okay, this is for 0 to 1, and then we can use it to check. We can use it to check it with our solution for the integration of the arc length. Okay. So we have 2t plus or it will be 6 over 3 plus 1. So it will be 7 over 3. Okay. Okay, I hope you get it. And then find the curvature. So let me write here. And maybe let me move number 3 be around here. So the curvature, if you want to know how to pronounce this, this is called the kappa. Not the kappa like in Japan mythology, but kappa in I think Greek. Okay, Greek. So the curvature is okay. So we need to find the unit tangent vector and the first derivative. Okay, maybe we need to find the first derivative. That's easy to find, right? We just differentiate, becoming 5 cos and then negative 5 sine. And then we need to find the value. So 5 cos squared plus 25. Let me just write all. Okay. This 2 becomes 25. So plus 1 is 26. So it's 26. So first, write the tangent vector is and then we differentiate the unit tangent vector. Zero and okay. And we also need to find the value from that unit tangent vector derivatives. This will be 25. sine squared t plus 0 plus 25 cos squared t. And it's all divided by, yeah, this square root of 26, right? Okay. So this will be 5 divided by square root of 26. So the curvature is 5 over this divide with this. So we have, okay. So yeah, basically you need to be careful when you are doing all this curvature, unit tangent, normal, binormal. So if you are not careful from the early calculations, you will not get the answers. Okay, guess you get maybe wrong here, or more, maybe wrong at the tangent vector. Okay. Now find the normal vectors. Oh, sorry. Number 3, this should be at the given value. So at given value of 1, 2 over 3, and 1. Okay, sorry. So after you get the calculations, you need to put on all the points. So from here, from the point here, if you want to look at the positions, we can check whether it's correct or no. So when t equal 1, this is correct, right? And it's also correct here. So t is equal 1, corresponding to the coordinate. Okay. So first, the tangent, the unit tangent vector. Let me just write all the necessary formula for you. So we need to put on and look for the unit tangent factor at t equal 1. And the normal is okay. And by doing so, we are calculating at t equal 1. Okay. So if you want to look at the first derivative, is 2t 2t squared and 1. And then the length is 40 squared plus 44 plus 1. This also we can see that this is actually 2t squared plus 1. Yeah. So we can cancel this, and this will be 2t squared plus 1. And plug in 1 so that you can find the tangent vector is or this is 3 if you plug in t equal 1. Okay. So this will be 2/3, 2/3, and 1/3. Or this if you need to, but I think you don't need to count this. Okay, so let me put this. This is no need. Okay. If the question is asking, then you can write that. We can just go directly to here. So the T, we can just write all the formula. And we can look for the first derivative of T. So we can do it by let me check this. Maybe you can change to this to make it better viewing for your calculations. And each one of them use the quotient rule and find the T prime. You will get this is I'm not sure this is correct or no, but later I will check. But at least this is what you need to do. So finding T prime and then find the length. Find the length and plug in all T. So plug in T equal 1, and then you will get the normal factors at T equal 1. Okay, I think that's it for the exercise. Please check the Google Classroom. I have several exercise for you to check and try. If you don't have any questions, so I will finish up until here. Okay, and please don't forget to send an email from your GApps account. Okay, send an email from your GApps account. You can check the Google Classroom if you forget. But if you want to send it now, please send your name, your student ID, your calculus class. Okay, and send it to my GApps. Okay, send it to my GApps. I've written down the information on the chat box. Please check the chat box, or if you want to check later on Google Classroom, you can check the Google Classroom. I wrote the same informations. Okay, I wrote the same information on the information on the Google Classroom. You can check the stream. You can check the stream and check the assignment also. I will add the assignment for maybe some for a grading part later. Okay, if you don't have any questions, so I will stop the recording and you can leave the meeting.